Okay, this is one of the harder lessons that I teach because it's a hard concept to understand. So I'm going to need you guys to fully commit to today to understanding. We are going to let's go ahead and write the rule first. Okay, so if a population is, well, this one is if a population is normally distributed. So if it looks like a bell curve. Then, if you take samples of any size, the sampling distribution of the sample means is also a normal distribution. But if a population is any shape, not just a bell curve, but any shape, and you take samples where the sample size is greater than or equal to 30, then the sampling distribution of the sample means is approximately normal, which I'm sure at this point makes no sense to you. So let me try to explain. Okay, let's say that I was like asking 5 people at a time what their GPA is and finding the average, okay? If I listed everybody in the school's GPA, I'd have between, well, that would be more normal distribution, but I'd have between what, 0 and 4, right? Some people would have 0, some people would have 4.0. Okay, now let's imagine that instead I took groups of 5 people and I averaged their GPA. So now I have a whole bunch of means as my data. Like each number, 3.2 is the average of 5 people, and this one's the average of 5 people, and this one's the average of 5 people. If I graph those, they're also a bell curve, but it gets tighter. Does that make sense? Because it'd be super unlikely that you'd have 5 kids that all have 4.0s or 5 kids that all have 0.0s. So instead of having a bell curve, look at my hands, instead of having a bell curve that's stretched out like this, it gets like narrower and taller, where the trending is more towards the middle. Is that making sense to you guys? But even if it was originally like a flat distribution, if you start taking samples like 5 at a time or 30 at a time, and you get all those means, no matter what, it will look like a bell curve. And I'm going to show you an example of that down here. So let's imagine that we had slips of paper in a box, and the numbers were 1, 3, 5, and 7. And you randomly select 2 pieces of paper, and you can put them back. Okay, so one option is you picking a 1 and then a 1. One option is a 1 and then a 3, 1 and then a 5, 1 and then a 7. What's another option? 3, 5. I'm going to write 3, 1, 3, 3, 3, 5, 3, 7. Okay, give me another. 5, 1, 5, 3, 5, 5, 5, 7. Last list is 7, 1, 7, 3, 7, 5, 7, 7. Okay. Now if I said, what are your chances of getting this? And you just had one piece of paper. You could get a 1, a 3, a 5, or a 7, and your chances of getting each one is 1/4. So you can imagine that it's just like a flat line, right? Like you could get a 1, a 3. Here, I'll show you. Here's the probability. So 25% of the time you'd get a 1, 25% of the time you get a 3, 25% of the time you get a 5, 25% of the time you get a 7. Everybody okay with this so far? But now I'm going to start getting groups and finding the average. What's the average of 1 and 1? 1. What's the average of 1 and 3? 2. Average of 1 and 5? 3. Average of 1 and 7? 4. 1 and 3? 3 and 3. This one's 4. This one's 5. 5 and 1, average is 3. 5 and 3, the average is 4. 5 and 5 is 5. 5 and 7 is 6. 7 and 1 is 6. 7 and 3 is 5. No, this one is wrong. 4. 7 and 5 is 6. 7 and 7 is 7. Everybody understand how to do those? To find the averages? Okay, now if I start thinking about what are the chances for each one, what are the chances to get an average of 1? Well, I've got 1 here out of 16 choices. 1/16. 2. 1, 2. 2 out of 16. 3. 1, 2, 3. 3 out of 16. To get an average of 4. 1, 2, 3, 4 is 5 out of 16. 5s is 1, 2, 3, back down to 3 out of 16. Wait, no, 4 was 4 out of 16, right?
Yeah.
5 is 3 out of 16. 6 is 2 out of 16. And 7 is 1 out of 16. So you see how when I start doing the mean of the means, it is way more likely that I get a number in the middle, like 4, which makes sense because we've got averages of many different things. So even when I take a sample of 2, again, the original distribution looked like this, grabbing just 1 at a time, 25%. But then if I grab 2 at a time and look at all those means, do you see how it starts making a bell curve? And it's going to make a bell curve more often and more often than that. So the following formulas are true then. This is called the mean of the means. So it's like a mu with a sub x bar. Mu sub x bar. This is called the mean of the means. The mean of the means is going to be exactly the same as the original one was. It's still mu. And the standard deviation of the means is the old standard deviation divided by the square root of n. So this is the mean of the means. This is the standard deviation of the means. Is going to get smaller. Remember how I told you that, like, look at my hands. If you have a wide bell curve, it's going to tighten it up, right? Make it taller and shorter. That means the standard deviation gets less. And the variance of the means is just this one squared, which I guess you could call sigma squared over n.
What's your N?
What?
What's
N
N?
is your sample size.
Oh,
Like how many, like remember how I was taking groups of 2?
yeah.
So that, how many are in each group? Good question. Okay, so if I jump to the second page, and I say, okay, so cell phone bills for our residents of a city have a mean of $47 and a standard deviation of 9. So this is the mean is 47, and the standard deviation is 9. Random samples of 100 phone bills are drawn from the population, and the mean of each sample is determined. Find the mean and the standard error. Let's go back to the front page. The standard deviation of the means is also called the standard error. Okay,